Welcome. In this session, we'll learn what happens, how do we represent R and C phasor domain. Okay, let's start with the resistor R. Let's start with resistance. Okay, so let's suppose this is our resistor, and in time domain, let's suppose the voltage across this resistor is V of t, and R is the resistance, and the current flowing at this instant of time is I of t. So we know by Ohm's law, voltage and current in resistor is related as V of t at an instant of time is R, resistance time is the current. This is referred as the Ohm's law. From Ohm's law, we write the voltage in terms of current like this. Now let's suppose I of t is given as I of m cosine of omega t plus theta. Okay, this is the current at any instant of time t. Now in phasor representation, we can write I phasor as I at an angle of Im theta. Okay, I phasor can be written as Im amplitude at an angle of theta. So what will be V of t from this if we substitute I of t? So V of t will be simply equal to R times I of m cosine of omega t plus theta. Now, if we substitute the phasor of this, so this is the current at any instant of time. So if we substitute the phasor of this phasor representation of I, we'll get the phasor representation of voltage. So V phasor will be simply equal to R times I am at an angle of theta. Okay. So V phasor is simply equal to R I am at an angle of theta. So we can write it as V is simply Vm at an angle of theta, where Vm is simply R times Im. Okay, where the amplitude of this V phasor is simply resistance multiplied by I phasor. So what is the relationship of V phasor with I phasor? If you look at this, V phasor and I phasor here are in phase. The phase difference means what is the phase of voltage? Theta V is equal to theta. Similarly, what is the phase of current? Is theta. So what's the phase difference? Theta V minus theta I in resistor is theta minus theta, that's equal to 0. So the phase difference between voltage and current in resistor is 0. This is very, very important. In other words, the voltage and current in a resistor are in phase. So if we draw the equivalent circuit of this resistor in phasor domain, we can write it like, say, this is V is related to I. From this equation, we can write from here, we can say V is equal to R times I phasor, right? So what's the relationship? So we can write V is equal to I phasor times R, okay? So in other words, V phasor and I phasor are related by R, okay? Now V phasor by I phasor is referred as the impedance offered by the element. So this is the impedance. Definition of impedance is in an element is simply that is denoted by Z, that is denoted by V phasor divided by I phasor. Now V phasor is R times I phasor divided by I phasor. So I and I cancel, so we are left with. So impedance offered by a resistor is simply R. So in time in when the voltage and currents are varying with respect to time, the impedance offered by the resistor is simply R. Okay, same like in DC circuits. Okay, this is the literal definition of impedance. Impedance is simply defined as V phasor divided by I phasor. Here V phasor is R times I. So I and I cancel, so we are left with this. Okay. So if we draw the phasor diagram of this voltage and current in for a resistor. So if we draw the complex plane first, so this is real axis, this is imaginary axis. So this is the real axis, this is the imaginary axis. So if I phasor is on this direction, so I phasor is having some phase theta, what will be the direction of the V phasor? Because there is no phase difference. In other words, the V phasor will also be in the same direction. So if this is I phasor, V phasor will also be in the same direction because V phasor is equal to R times the I phasor from here. You can check it on this. Okay, so as there is no phase difference, so if I is oriented in this direction, V will also be oriented in this direction. And if I rotate this, okay, I'll say I is my reference. So if this is I is the reference in the circuit, so I is in this direction. Where will be V located? V will also be in for a resistor. V will also be in the same direction. So this is the phasor diagram of a resistor. In other words, this is very, very important. Voltage and current in a resistor are in phase. So there is no phase difference between voltage and current as far as resistor is concerned. Okay, now let's study the inductor. So let's study the inductor. Now let's suppose we are given this inductor where voltage in time domain v of t like this, and the current is flowing like this, I of t, and this is it. Now how is v and I related in inductor? We know v of t is L dit by dt. Okay, now let's suppose I of t, the circuit, I of t is simply Im cosine of omega t plus theta. Okay, now this can be written in phasor. What is the phasor representation of this current here? I phasor is simply Im at an angle of theta. Okay, this we learned in the previous session. So substituting the value of I of t here, what will be V of t? V of t will be simply equal to L d by dt of Im cosine of omega t plus theta. Im is a constant, so this will come out of this differentiation. So if we do the differentiation of cos x is minus sine x, so it will be L Im sine of omega t plus theta. Now then internal differentiation of omega t plus theta will be equal to omega. So multiplied by omega. So multiplied by omega here. Okay, so we can write this as minus omega L Im sine of omega t plus theta. Now we can write this as omega L Im cosine using trigonometry. We can write this as cosine omega t plus theta plus 90 degree. Cos theta plus 90 degree is minus sine theta. Okay, that's what I have used it here. Now, if I write the V phasor from this, if I write the V phasor for this equation, so V phasor will be simply equal to amplitude. Amplitude here is, this is the amplitude of this cosine wave. So that is equal to omega L times Im at an angle of theta plus 90 degree. Okay. So Im at an angle of omega L, Im at an angle of 90 theta plus 90 degree. So we can write V is omega L times Im. I'll break this into two terms. Im at an angle of theta, 1 at an angle of 90 degree. We know we can, in multiplication, we can simply multiply the magnitudes and add the phases. Sorry, this is not 90 degree, this is theta. This is theta. So theta plus 90 degree. Okay, we learned this in the previous sessions, how we can multiply two complex numbers in polar form. Now, what is this? This is I phasor, right? So if you look at this is the I phasor, right? So V phasor in terms of I phasor can be written as omega L times I, 1 at an angle of 90 degree. Now 1 at an angle of 90 degree is same as e to the power of j 90 degree, which is same as if you use Euler's identity, cosine 90 plus j sine 90, which is equal to j. Okay, so for this I will substitute j, so this will be j omega L times I. Okay, so this is how voltage phasor is related to current phasor in inductor. Voltage is j omega L times I. Okay, this is very, very important. All right, so first of all, what is the relationship between V phasor and I phasor? Now, if you look at this, V is related to I phasor by this expression. Now, what is the meaning of this? On this equation, the voltage in leads the current by 90 degree. In other words, voltage is ahead of 90 degree in inductor. That's the meaning of this, that voltage phasor or voltage in inductor is simply ahead of 90 degree to current in this. That's the meaning of this term. Okay, that's the meaning of this. Okay, so voltage in inductor leads the current by 90 degree. That's very, very important. And also the impedance, we know the impedance is defined as impedance offered by this inductor. Yes, that is denoted by Z. Z is simply V phasor divided by I phasor. Now, if you substitute V phasor here, V phasor is j omega L times I divided by I. So that will be j omega L. So the impedance offered by the inductor is simply j omega L. So impedance offered by the inductor is j omega L. And another thing we learned is as voltage leads the current by 90 degree. In other words, if we draw the phasor diagram of this inductor between voltage and current, so if we draw the general complex plane first. So this is the complex plane. This is the imaginary axis. This is the real axis and imaginary axis. So if I say the current phasor is like on this direction, okay, current is like in this direction, so this is I phasor. Now where will be V phasor? V phasor is leading the voltage by 90 degrees. So V phasor will be in this direction, will be ahead of this by 90 degree. So this will be the direction of V phasor. That's the meaning of that it is ahead of this by 90 degree. Okay, now I can also draw this. We can also draw this if we assume the current is the reference, means I'm measuring everything with respect to current. So if this is I phasor, where will be V phasor? V phasor will be on this direction. Okay, now here I am assuming I is the reference. Here I am assuming real axis is the okay. And what is this theta? This angle equal to this is theta. Okay. Here I am assuming my reference here is this current. Okay. That's the difference between two diagrams. This is the general complex plane, but here I am assuming I am starting with the current as the reference axis. I hope you understood. So what we learn that current lead is voltage lead is the current by 90 degree. In other words, current lags the voltage by 90 degree. So what is the phase of voltage? If we say phase of current is theta I, is simply if theta I is theta, then what will be the phase of voltage? Theta plus 90 degree in inductor. So what will be the phase difference between voltage and current? Just theta plus 90 degree minus theta, that's equal to 90 degree. So the phase difference between voltage and current in inductor is this, and this is the phasor diagram. Okay, this is the general complex plane. This is assuming that our reference is current. Okay, all right. Now next we'll talk about capacitor. How is V phasor related to I phasor in capacitor? Okay. Now let me first draw the phasor circuit of this inductor. If I have to draw the phasors equivalent of this, how is V phasor related to I phasor? We derived that V phasor is related to I phasor by this expression. So if we say capital V is the V phasor and current is I, then inductor will be simply replaced by j omega L. So inductor will be replaced by j omega L or simply omega L at an angle of 90 degree because J is simply 1 at an angle of 90 degree. So that's how we replace the inductor within phasor domain, j omega L. Next, let's talk about capacitor. So let's suppose we have a capacitor. The voltage and current is given as V of t and current is I of t. C is the capacitance. So how is I of t related to V of t? We know that current I of t, current in capacitor at any some time is C dVt by dt. Now let's assume the voltage in the capacitor is given as V of t is Vm cos omega t plus theta. Okay. So this is our this current voltage at any instant of time. Now we can write this in the phasor form as V phasor will be equal to Vm at an angle of theta. So this is the phasor representation of this voltage. Now let's substitute this IV of t in this expression. So we'll get I of t will be equal to differentiation of this. Let's do it directly. So it will be Vm differentiation of cosine omega t plus theta is simply minus sine omega t plus theta multiplied by omega, right? Internal differentiation of omega t plus theta. Now, if we can write this as minus omega c Vm sine omega t plus theta. Now, if we use trigonometric formulas, we can write it as omega c Vm cosine of omega t plus theta plus 90 degree. Okay. Now if I write I of t in phasor form, so I'll say I phasor is equal to omega c times Vm at an angle of theta plus 90 degree. What's the phase here? Theta plus 90 degree. I'll break this into two terms. So I'll write omega c Vm at an angle of theta 1 at an angle of 90 degree. So what's Vm theta? Vm theta is simply here V phasor. So if we replace Vm theta by V phasor, so I phasor will be equal to omega C V phasor at an angle of 90 degree. Right? This is 1 here. So 1 multiplied by omega C is omega C. What is this relationship? This relationship simply tells us that current phasor is leading the voltage by plus 90 degree. Current phasor is leading the voltage by plus 90 degree. In other words, voltage lags the current by 90 degree. That is one of the same statement. Current leads the voltage. So in capacitor, current leads the voltage by 90 degree, or voltage lags the current by 90 degree. That's one of the same statement. Okay. Now we can also write 1 at an angle of 90 degree, we can put as J. So I can say I is equal to omega C V phasor times J. So this we can write as I phasor can be written as J omega C times V. From this we can get V. V is simply I divided by J omega C. So this is the voltage and current relationship in phasor form. Okay. Now we know the impedance offered by the capacitor is defined as, so impedance offered by the capacitor is given as Z is V phasor divided by I phasor. So V phasor is I divided by J omega C divided by I and I cancel. So we are left with 1 divided by J omega C. So the impedance offered by capacitor is 1 by J omega C. Okay, so this is the impedance of that capacitor. And in phasor domain, the current leads the voltage by 90 degrees. So if we have to draw the phasor diagram of this, so first let me draw the general complex plane. So this is real axis. This is imaginary axis. So real axis and imaginary axis. Now if I say voltage phasor is on this side, so this is V phasor. So V phasor is making an angle of theta with real axis. So what will be the I phasor? I phasor will be leading the voltage by 90 degree. This will be I phasor. Okay, that's the meaning. Now if we take V as reference, okay, if I take V as reference, I can also draw it like this. So V phasor is like this. Where will be current phasor? Current phasor will be on this side, leading the voltage by 90 degree. So this is also the phasor diagram of capacitor. Similarly, I can also draw this. We can draw it like this. So if I say this is the current, if this is the current is on this side, where will it be the voltage? Voltage is lagging the current by 90 degree. Our current is leading the voltage by 90 degree. So current will voltage will be on this side. That's again the valid phasor diagram of this capacitor. So all three are one and the same. The only difference between this and the other two are that we also drawn the complex plane here as well. Okay, so this is the general phasor diagram. So how is V phasor and I phasor related? So if I have to draw the electrical equivalent here, so if I have to replace the capacitor in phasor domain, how is V phasor and I phasor related? V phasor and I phasor are related by this expression. So if the voltage, that is the V phasor, is plus V and the current I is capital I, then capacitor will be replaced by 1 by J omega C. Okay. So what we have learned so far, we have obtained the phasor diagram of three elements R, L, and C. So what we have noted, first point that we observed is V and I are in phase in resistor, are in phase in R. Second point that we have observed in terms of phasor is voltage leads current in inductor by how much? By 90 degrees. Similarly, in capacitor, I leads, that is the current, leads voltage in capacitor by 90 degrees. Okay. Now you can also replace the leading statement with the lagging. So current lags in inductor, current lags in this capacitor, voltage lags. Okay, that's one and the same step. Okay, so let's summarize the impedances. Also, one more quantity. Impedance is defined simply as Z is defined as V by I. Another quantity that's very important for us is called the admittance. Admittance is defined as inverse of impedance and it is denoted by letter Y. So it is defined as inverse of impedance. So if you substitute this V by I here, it will be current divided by voltage. Okay. So let's summarize the impedances of the elements, this table. So element, the element in time domain. Time domain representations are time domain relationships, frequency domain are phasor domain relationships between V and I, and what is the impedance and so Z means the impedance and what is the admittance of the element. So first element is a resistor. How is V and I related in time domain? Is simply V of t is simply R times I of t in time domain. Current at and voltage at any instant time is resistance multiplied by current. Now in phasor domain, simply V phasor is equal to R times I phasor. Okay, so what's the impedance? Impedance is defined as V by I. V by I will be simply equal to R. So what will be the admittance? Inverse of R, right? 1 by R. So admittance offered by the resistor is 1 by R. Then we have inductor. How is V and I related in inductor? So V of t is L dit by dt. How is the phasor voltage and phasor current related? V phasor is equal to J omega L times I. So from this we'll get impedance will be simply equal to V by I, that's equal to J omega L. So what will be the admittance inverse of this? That is 1 by J omega L. Okay, now last element is capacitor. So how is the voltage related here? I of t, current at an instant of time, C dVt by dt. How is voltage phasor and current phasor related? V phasor is equal to I divided by J omega C. So what will be the impedance offered here? 1 by J omega C. Similarly, the admittance Y will be equal to J omega C, inverse of this impedance. All right. So this is how we write the elements in phasor domain. All right. Now next, let's solve some few examples on this. Okay. Now the first question, first example that we'll talk about is given a voltage, we are given a voltage phasor V that's equal to 800 at an angle of minus 50 degree at a frequency of So frequency, that's omega, is given as 100 radians per second. So omega is given. Now voltage, we are given the phasor voltage, that's equal to this at an angle of 100 radians per second is applied to an inductor of 4 Henry. Okay. Now what we have to do, we have to determine the phasor current and time domain current. Determine the phasor current and time domain current of this inductor. Okay. So to solve this, we are given V phasor. V phasor is 800 at an angle of minus, and inductance L is also given 4 Henry, and L is given 4 Henry, and omega is also given how much? 100 radians. Okay. Now we know what is the relationship between V phasor and I phasor. We know V phasor is equal to J omega L times I. Now we are given V. So what will be I equal to? I is simply V divided by J omega L. So substitute the value of V. V is 800 at an angle of minus 50 degrees divided by J. Omega is 100 and L is 4. So this is 800 at an angle of minus 50 degree. Now this is 400 J. 400 J. Now J can be written as 1 at an angle of 90 degree. In polar form, we can write it as 400 at an angle of 90 degree, because J is simply 1 at an angle of 90 degree. Okay, so 800 and 400. If you divide 800 by 400, that will be equal to 2 at an angle of, what we do with phases in division, we subtract the phase. Okay, minus 50 minus 90. So this is our I phasor. So what's I phasor equal to? I phasor is simply 2 at an angle of minus 140 degree. That was the first part of this problem. Find the I phasor. Next, we have to write this in time domain form. So what's the time domain equivalent of this phasor? I of t will be equal to amplitude. Amplitude is 2 cosine of how much is omega? Omega is 100. T plus omega is given this time. This is minus 140. So let me write minus here. Minus 140 degree amplitude. Amperes. Okay. This is in ampere. So this is the current in phasor format. This time domain form. All right. So this was the first problem. Now, second problem is find what we have to do. V of t applied across a capacitor is given by voltage applied across a capacitor that is equal to 10 cosine of 10 cosine of 100t plus 30 degree. And capacitance of the capacitor is also given, that is 50 microfarad. Okay. Now we have to find the voltage via I of t. So our goal is to find I of t. So first let's apply the phasor equation. So V of t is 10 cos 100t plus 30 degree. Now in phasor form, we can write this as V is 10 at an angle of 30 degrees. Okay. Now we know how V and I phasor are related in capacitor. V phasor is simply I phasor divided by J omega C. So we have to determine I. So I is equal to J omega C times V phasor. Now J omega is, if you look at this problem, omega is how much? Omega is 100 here. So 100 multiplied by capacitance is, I think, 50 microfarad. Yes, 50 microfarad. 50 microfarad is 50 into 10 to the minus 6. V phasor is 10 at an angle of 30 degree. 10 at an angle of 30 degree. So how much will be this? This is J 50. That's 500. So this is 50,000 multiplied by 10 to the minus 6 at an angle of 30 degree. Okay. First, let me evaluate this part first. So this I can write as J into 50 into 10 to the power minus 3 at an angle of 30 degrees. So J can be written as 1 at an angle of 30 degree. So this is 50 into 10 to the power minus 3 at an angle of, sorry, this is not 30 degree, this is 90 degree. J, we have already learned, J is simply 1 at an angle of 90 degree, which is same as 1 e to the power of J 90 degree. Okay, we learned in the previous class. So this is the I phasor. So we are given multiplication of two complex numbers. So 1 multiplied by 50 into 10 to the power 3, that is 50 into 10 to the power minus 3. Now angles will add simply. This is 90 degree plus 30 degree. So this is 50 at an angle of minus 3 at an angle of 120 degrees. So we can also, this is in amperes, we can write it in milliamperes. I is simply 50. I is simply here 50 at an angle of 120 degrees. Now we'll change the unit to milliamperes. 10 to the minus 3 means 1 milliamperes. Okay, this is in phasor form. Now I of t from this will be simply equal to amplitude is given as 50, cos omega is given, I think, 100 t plus 120 degrees milliamperes. Remember the unit here is milliamperes. So this is what we needed to find. Now one more problem based on this phasors is, let's assume the voltage across the inductor. Inductance is 0.1 Henry. The voltage applied across this is V of t, that is given as 12 cos of 60t plus 45 degrees. Okay. So a voltage applied across an inductor of 0.1 Henry is this. Find the current. So our goal is to find what is the current flowing through this inductor. So voltage V of t is given as 12 cosine of 60t plus 45 degrees. So we can write this as in the phasor form, that is 12 at an angle of 45 degrees. Okay, so omega here is 60. Omega here is 60. Okay, now we know the voltage phasor and I phasor are related in inductor by j omega L times I. So we need to find I. I will be simply equal to V divided by j omega L. V is simply 12 at an angle of 45 degrees divided by j, let me keep j as such, omega is 60 multiplied by L is 0.1 Henry. Okay, so 12 at an angle of 45 degrees by j multiplied by 6. 60 multiplied by 0.1 is 6. Now 6 divided by 12 divided by 6 is 2. So we can write it as 2 at an angle of 45 degrees divided by j. Now j in polar form can be written as 2 at an angle of 45 degree divided by 1 at an angle of 90 degrees. So this is the current phasor. 2 divided by 1 is 2. What we do with phases, phase we subtract. Okay, so this can be written as 2 at an angle of minus 45 degrees. So this is in phasor form, but we need to find I of t. I of t can be written as, what is the amplitude? 2 cosine of omega is 100, not 160. Omega here is, I think, 60. Yes, omega is 60. T minus 45 minus 45 degrees. So we needed to find the current flowing in this. Okay, this is the current. All right. So what we learn in short here, what happens to RL and C in phasor domain? Okay, R gets replaced by R in phasor domain. Inductor is replaced by J omega L, and capacitor is replaced by 1 by J omega C. Okay. Then we learned the impedances of these elements, and we solved few examples. Okay, let me end this session here.